Okay. Question and answer session today. Chapter 1, Section 3 on modeling and creating models, and Chapter 2, Section 1, solutions without actually solving. What questions? You just have to give it back to me when you have somebody asking questions. Like, read it. There, that way I know which question's there. Okay.
I was just trying to make sure these.
That is always important, yes. The book bundle people effed up. And that's why some of you got an email saying, hey, here's a link if you're willing to switch to the ebook. But if you are not part of the book bundle, make sure you are getting the correct edition. That's why the ISBN is in the syllabus, so you have the exact version of the book I've got. Whether you get it electronically or not, that's up to you. But a lot of things turn very interesting when you order books off of Amazon, because you can get the international version for like $7 or something, and then all the questions are different. One of the interesting things I found when I was teaching calculus is that the international versions are only in metric. There's nothing in feet, inches, pounds, none of it, because they're all for the international market. Anyhow, questions? Yes.
On 143.
Let's feel this for a second while I read that question. Number 4. Well, we have to do number 3, which I think means we have to do number 2. So we're going to do a bunch of these problems. Let's see. Let's at least read this. The population model given in 1 fails to take death into consideration. Growth rate equals birth rate. So we could look at the population with net change. Birth rate is proportional to the population present at time t. Death rate proportional to the square in problem 3. Problem 4 says, what happens if we have a harvest? So let's look at problem 3. Problem 3 says, determine a model for population if birth rate is proportional to the current population, death rate is proportional to the square of the population. So, change in population over time is proportional to birth rate. Okay, but it gives me birth rate and death rate. Wait a minute. Change in population. There's the easy version, right? Change in population, how many new people came in, how many people went out. This sounds like the mixture problem. Salt in minus salt out, people in minus people out. I think we're talking about fish at some point here. So same idea. But now we're told specific things. Births are proportional to problem 3. So there's some constant for births times the population. And what about the death rate? So there'll be some other constant and the population squared. That's all I got at this point, is that number times population to add in and number times the square of the population to pull out. Now, I hope that that KD for deaths is much smaller. Because when I have a large population, P squared is a lot bigger than P. So if this I hope is a much, much smaller constant so that my population doesn't die out very quickly. What's question 4 saying?
3. That rate in which the population certain fish changes by also assuming that the fish are harvested at a constant.
If I own a fish hatchery and I just keep letting them breed, eventually I'll have solid fish, right? No water left, just a block of fish. Doesn't work like that, right? And if I'm having a fish hatchery, I want to do something with the fish. Sell them, eat them, whatever. I have to take some fish out. I have to harvest a bunch of fish. I don't know what that rate is. They called it H, right? And it's independent of how many fish are in the pond. It says I'm harvesting at a constant rate. So every week I pull out 1,000 fish and sell them off. What do I do with that H? Does it get added to my population or subtracted from it? There's my model. I don't have to solve squat. I just have to write down why I've got this model and what justifies each of those pieces.
Not.
Did it say it was? Harvested at
It's
a constant rate. That, by the way, the fact that that's not related to population makes actually solving this harder. Actually figuring out the correct answer for this problem now just got harder. Jack, you don't look like you're happy about this.
That's it.
And explain why you wrote what you wrote. This is the best part about constructing a model. All I want you to do is explain to me why the equation you are writing down is the one you think is the right one. And in some cases, it's a matter of knowing enough about the outside situation. Like, I don't know very much about fish harvests at all. I was on a tour of Alaska 10 years ago, and we went to a fishery, and I got to watch it. That's all I know. But they talked about critical population thresholds, low end and high end. And in the back of my head, I'm laughing because, yeah, this is the differential equations course. My wife is telling me to shut up. But even if I don't know something, as long as they give me sufficient information for me to construct the pieces that went in based on what they told me, I think this is the equation I should get out. Justify why each of those things are in there. More questions.
good. So for number 2, it says determine a model for the population. Will I be able to leave it as the differential equation, or will I have to like take and do an integral to get?
To try and solve it?
Yeah.
Well, the fun part is that we don't necessarily know how to solve that equation yet. It just says find a model for the population. We can use the differential equation as the model. You could leave it like this. Find an equation for the population, I think might be a different story. Especially since even in the very next section, we don't talk about how to solve any of this yet. I would like to know how to solve this equation. And I think that's what we do on Friday. At least for this one. Here is a giant hint. Go reread Calc 2, Chapter 7, Integration Techniques. Go do a bunch of animals. There is a reason this course is called Calc 4 with differential equations. More questions. 1.312. Hang on a sec. So 12 requires me to have, I think, 10 and 11, right? Oh, no, it says generalize the model in 8. So let's go back to example 8. That's our mixing model for the salt in the tank, right? Yes, here we go. Here's the model number 8. There's my equation. That's the mixture problem. So now I can read what they want me to do with that problem. Generalize by assuming the large tank initially contains some number of gallons, rate in and rate out in gallons per minute. Okay, wait a minute. Number 12. Tank. Starts with N0 gallons of brine. Now that's a saltwater mixture, so I might have some salt to start with. R in and R out. R in, R out. Gallons per minute. Gallons per minute. C in is the concentration of the salt going in. C in, concentration of salt in. C of T is the concentration in the tank. C of T, salt concentration at time T in tank. Outflow measured at time T as well, and out. A of T is the amount of salt in the tank at time T. Okay, the worst part about this entire problem is the fact that absolutely nothing in this problem, Jalen, has any numbers in it. All right, fine. A concentration of salt. What are the units for that? If I was a chemist, I'd say molarity, but I'm not. But pounds per minute is a rate, right?
Oh,
Well, pounds would be an amount. Concentration. Wait a minute. I'm going to measure some of the water and I'm going to tell you how much salt is in it, right? So it'd be salt per water. So I think the right unit for this is pounds per gallon. Like it would be moles per liter if I was a chemist. So I'll say the same thing up here for C of T. That's pounds per gallon. And A, that's pounds. So now I have units to go with everything. Talk to me.
I
Jalen?
would say that like on onset, think of times instead of A of T. No R is going to. Or R in like.
R in is gallons per minute, right? So that's stuff flowing in.
Right. Since I guess start in not that's how much start.
That's how much liquid I have, right? That's the gallons. That's just gallons. But let's go back to the model we used. The model we used measured the change in the amount of salt. Because I have salt coming in and salt going out. That's change in salt. That's dAdt. So I think I actually want to start there. I want to start by trying to figure out how to write this equation. Salt in minus salt out. If I'm doing salt in, what should the units be on that? If the units on salt is pounds, what unit should DADT have?
Pounds per gallon. Pounds per minute.
Because it's DT, it should be pounds per minute. So this should be pounds per minute. And that means that whatever's over on this side with salt in and salt out should end up being in pounds per minute. So let me start with salt in. Because everything I want to know about salt in is here. In those numbers right there. This box. That's my entire in. I need to make this unit out of this information. How do I make pounds per minute out of this information? Yeah. I have gallons per minute. Multiplied by pounds per gallon, which is what I have for concentration. So salt in is the concentration in times the number of gallons in per minute. Pounds per gallon, gallons per minute. I get pounds per minute. Perfect. It is, at this point, this is a stoichiometry problem 100%. Out. Out's going to be harder. So, to think about out, I need these numbers. So let's again think about getting the units right. I have an outflow, gallons per minute, which means the other piece of information I need is pounds per gallon. Where do I get pounds per gallon? I saw concentration. But that changes, right? That's that C of T thing. That's a function. So the amount of salt coming out should be concentration times rate, yes? Concentration times rate. Well, that just looks like it should look like that R times C thing again, right? Where's the tank itself come into the game? Concentration, pounds per gallon, times rate out, gallons per minute. That's pounds per minute. That's exactly the thing I need. But this is in C. And this is in A. And that's not helpful if they're two different variables. I really would much rather have that as A, not C.
But
Multiply what?
see, so
Okay, wait a minute. C is concentration. That's pounds per gallon. If I multiply by gallons, that gives me pounds. Then my units won't work to get this to be pounds per minute. If this is suddenly in pounds, that's not going to help me because then the units don't write out. I still want whatever this thing is to be pounds per gallon. No, I'm still only talking about the salt out. I don't want to change salt in because I'm pretty sure we got that one right. There's only one hose coming in, then there's all that mixing going on, right? Wait a minute, wait a second here. C of T is a function. And we don't know. But what we do know is that we're looking for discussion of A of T. And A of T is pounds of salt. And you just said it. Pounds per gallon times gallons would give me pounds. What if we went the other way? And I asked, can we rewrite this in terms of A? A is pounds. What do I need to account for to get the right unit? Gallons. And I know how many gallons the tank is. So it's actually going the other way. And I want pounds per gallon. That's the amount of salt in the tank divided by the number of gallons in the tank. So I actually have hiding right up here an expression for C of T. C of T is really A of T over the number of gallons in my tank. That's a number, N0. I don't know what it is. I think in the example, the tank was 300 gallons yesterday. I'm sorry, Friday. That would have been Friday. I think it was 300 gallons, but it could be any size. It could be 100, it could be 7,000, it could be 3 million gallons. But I need to know how much salt is in it. That's A. And then I need to know the number of gallons. This is now pounds per gallon, gallons per minute. That's pounds per minute. So I can now take this equation, put this in here, and I have dA dt is concentration in times rate in minus concentration out times rate out. But I'm not writing it in terms of this mystery variable C. I'm writing it in the same function A that we started with. So now I'll have one Y variable, A of T. Yeah, there's a whole lot of stoichiometry in here, isn't it? By the way, I can just switch those two by place, right? And I'd have number minus number times A. Isn't that exactly the equation we ended up with in 8? Number minus number times A. Jalen, does that help? Or was that just way too much work?
no.
I am a defrocked physical chemist. I was studying physical chemistry before I was a math major. Physics and chemistry The only thing I absolutely 100% remember, absolutely stone cold, make the units match. That's the key to almost all of these modeling setups, make the units match. More questions, ask me more stuff. Somebody with an open computer, Google for me, the Atlanta Aquarium. Atlanta Aquarium is one of the biggest aquariums in the country. I think it might actually be the largest saltwater tank in the country. How big is the tank at the Atlanta Aquarium, the whale shark tank?
6.3 million gallons.
6.3 million gallons. Okay, I believe that there are something around 25 gallons per cubic foot. So say 4 cubic feet for every 100. We've got 6 times 10 to the 6th. Divide that by 100, multiply by 4. 6 times 10 to the 4th, 2.4 times 10 to the 5th. That's 250,000 cubic feet. The tank would fill Boyle Hall. They have 4 whale sharks in this tank. And they have plenty of room in this tank. It's a gorgeous idea, but the one whale shark would fill this room twice over. Picture 4 of them in this damn thing. How much salt do we need in the tank? What happens when you got to clean it? What happens when you have to filter it? By the way, there are thousands of other animals in this tank. Can you imagine what feeding time looks like? And cleaning up all the stuff that goes, the filter system that has to run for this thing. This is an amazing aquarium. It's been a very long time since I was there, but it made my wife very happy, so we'll go again at some point. This is not a useless problem. I don't want to just talk about the aquarium. I mean, I've got a home fish tank. If I'm going to run a saltwater tank at home, I need to do this exact same idea. Now, the best part is that I don't have to do the math. I can just do all of the testing strips and buy all the chemistry. The only fish I have in my house that survived, the stuffed version of the whale shark. Otherwise, forget it.
You do 25.
2.125. Probably. Okay, let me do something else real quick. 25 is not an assigned problem. 26 is. Good. 25. 25 says the first derivative dy dx is y squared times 4 minus y squared. Oh, we're going to actually do the pictures and the equilibrium solutions and all the arrows and stuff, right? Okay. Now, what you could do is you could just go to the computer, type this in, and say, here's the picture. But then I need to know if I got all the things I need in the picture. So let's do the analysis first. First question, what are the equilibrium solutions? Right. So now we're going to draw the phase portrait thing. You can draw it horizontally, you can draw it vertically. We're going to end up doing the horizontal one and then turning it into the vertical. So I'm going to make a number line. I'm going to put these things on here. Now tell me, where's the plus, where's the minus? And you could just plug in numbers, right? If you put in -3, you're going to get 9, and then 4 minus 9, that's plus times minus, that's minus. You put in 1, -1, you're going to get 1 and 4 minus 1, that's positive, and so on. Okay. So this means that I'm going down here. I'm going up here and up here and down here. But since that's y values, up and down became right and left. Up is to the right, down is to the left. Y up here, x down here. Y equals 2. Y equals -2. Y equals 0 is the x-axis. So far, so good? So the minus sign to the left of -2 there means that the arrows below -2 should be pointing down. The plus between -2 and 0 means those arrows point up. What about the plus between 0 and 2? Same thing. And above 2. Okay. Classify each critical point as stable, unstable, or semi-stable. Stable means both in. Unstable, both arrows out. Semi, one on each. Now, again, technically, those are asymptotically stable, asymptotically unstable, asymptotically semi-stable. That's how they behave as asymptotes as we go from left to right. Stable means we close in towards them. Unstable means we blow away from them. And semi, one side works one way, the other side works the other. By hand, sketch typical solution curves determined by this idea. So pick a spot. I'll make your life easy. Pick a spot on the y-axis. Right? You're going to pick a spot. We'll actually pick a number. So let's use like -2.5. That would be here. If I were playing follow the arrows, what would I be doing? I'd expect something that had this sort of picture. The further away we get, the more we're going to go away because it's unstable. We should blow up from it, right? You're looking at me like, did you do that?
No, I understand.
Okay. I should draw more than just one arrow. But the arrows that are going to be close are going to be fairly shallow, and the arrows that are further away are going to be steeper. So the further away I get, the steeper those arrows are going down. What about between these two? The closer I am to one of the asymptotes, the shallower the arrows are. So I start slightly above, I move up more and more and more, and then I start to level back out again because the arrows get shallow, steep, shallow. So I should see something looks kind of like this. It shouldn't curl back down at the end. That was a bad stroke of my pen. What should happen in the next block up between 0 and 2? The exact same thing. And above, it should come down this way. Now here is a ginormous hint. What's that graph look like? This is an algebra question. Does it help if I do this version? What's this graph look like? Starts out tiny, blows up gargantuan.
Like,
X squared goes like this.
so,
I heard somebody mutter. That's e to the x, right? Which means this one is e to the minus x. This one down here just kind of looks like an e to the x that turned upside down, right? There's got to be a lot of exponential going on in here. For me to get equations that look like this, that have these horizontal asymptotes, I've got to have something exponential going on when I actually solve stuff. I just haven't gotten there. But I expect these equations will have e's in them floating around.
So they, for all of those like phase, like solution, the solution curves, they all kind of like are similar. Like,
They're-
for all the different problems.
That's the best part. You really only get something that kind of looks like an exponential thingy, or something that looks like one of these long S shapes. We will eventually be able to show, eventually, that the steepest part is exactly halfway between the two solutions. And that means this curve is really symmetric. And if I shift it to the left or shift it to the right, it's the exact same curve, just picked up and moved over. So if you put one over here that goes through this dot instead, it's going to look like a parallel curve. Left to right, because there's no x in the equation. It's the same no matter how far left or how far right you go. That's what autonomous tells me. And this is why I like actually drawing the fields, the arrows on the computer. Because then I can just like, oh, well, whoosh, in, and there you go. I tend to like the drawings coming out of the grapher a little bit better than the drawings coming out of slopes. But that's because it's easier to manipulate the window on grapher than it is to manipulate the window on slopes. So I found. But that's why I put the recording of me doing this stuff on grapher on our Canvas page, so you could watch me do one. Plus the recording from yesterday. More questions? I will not make you draw a gazillion arrows on the exam.
we got 2.15.
2.115? Put the book over here. 15. 15 says sketch isoclines. Isocline, what the hell's an isocline? An isocline is a graph of the f of xy part. Wrong section?
No, just,
Oh, okay. 17. So this is another graphing question, and it says graph what's a null cline, which is where the function is equal to 0. So in this case, we have a function dy dx equals x squared minus 2y. Really, I can do both of these together. Because what we're talking about with an isocline is taking this part and setting it equal to some constant. And a nullcline is taking this and setting it equal to 0. So that's really the only difference between the two. You ready for the sneaky part? What I'm really asking you to graph is this equation. So let's rewrite it as y equals. What's the graph of y equals 1/2 x squared? A parabola. It's just not steep, it's a little wide, right? And then what does the minus c do? Well, it's probably easier if I write this like this. Which way does it move it? Up and down. So literally, if I have an equation, this should be an isocline. What the fuck is an isocline going to give me? It's a level curve. Remember when we graphed stuff in 3D, we would like, oh, you cut it this way and you get these pictures moving up and down? I'm telling you that this looks like parabolas. And as we change this value c, it goes up and down, which means the arrows should flow across these parabolas. These are perpendicular to our direction fields. The gradient.
Yeah, that's what it was.
We did this with the gradient. The gradient goes across these level curves. And that's how we did things like Lagrange multipliers and finding maximums and minimums. We looked at the gradient.
I remember.
That's why this is Calc 4 right after Calc 3, because we did that right there. That's the whole best part about this, is that these match up. There's really a 3D aspect to this. When we use the gradient, we talked about the fastest way downhill or uphill, right? The fastest growth. That's the way we change. Isn't that dy dx? Isn't that exactly what a derivative tells me? It's the right image. If we were to think about our direction field, I don't even know what the right equation is for this. I pulled one up that doesn't have an equation given to it. But those isoclines should be curves that these cut through at 90 degrees. At some level as we move from one spot to the other. So this surface is kind of twisty, isn't it? That's what I need to know. Better? Actually have a picture of those in here? No, they didn't give me the pictures of the isoclines. All right, which means I need to grab the calc book, which is on here somewhere. Click. Mutually perpendicular curves give me these things called orthogonal trajectories. There you go. That's the picture. Our gradient going across the red line, going perpendicular to all those level curves. That's exactly the thing I want to work with. See, here's our differential equation slope field. If I were to draw what's going on, I'd get circles, wouldn't I? Or some sort of oval going on in there. That's an isocline. You've seen this before. More questions? I'm 100% sure that the phrase isoclines and nullclines will be very, very, very rarely used by me moving forward. But it's worth thinking about because you've seen these on other maps. We think of a vector field moving stuff around like the wind. Well, then the isoclines are isobars, they're level pieces of barometric pressure. You think of a high pressure and a low pressure area, you have hot and cold. Well, then you've got isotherms, places where the temperature is the same. You've got physical level curves. Well, that's a topographical map that shows you mountains and valleys and all that stuff, and it's all the same height. Now we're just doing it relative to this differential equation. Same idea, different tape, different name, different tape. That one. So you're going to bring me this homework tomorrow? No, you're not. You're going to bring me this homework Friday, because tomorrow I don't see you all. But if you have questions, you should come bug me in my office hours tomorrow or Friday and send me email or whatever, and I will see you all then. Wonderful rest of the day.
What is your best today?
YouTube.